Hi everyone, today we're going to be talking about limits. Now, limits are a very important topic to learn when learning calculus. Let's jump into an example to see what a limit is. Example 1 says, consider the function f of x equals the absolute value of x minus 4 plus 3. Part A wants us to evaluate f of 7. So what that means is we want to take 7, and anywhere we see an x in our original function, we want to replace it with a 7. So we'll have the absolute value of the quantity 7 minus 4, and then plus 3. So 7 minus 4 is 3, so we would take the absolute value of 3, and then add 3 to that, which if we simplify that would give us 6. So f of 7 is equal to 6. Part B wants us to graph f of x on the axes provided below. So I'm going to label, that's my x-axis, and this is my f of x axis or my y-axis, whatever you want to call it. And I'm just going to rewrite the function really quickly. F of x equals the absolute value of x minus 4 plus 3. And then I'm just going to make an input-output table with x and f of x so that we can get some values in there. So let's see, 0, 1, 2, 3, 4, 5, 6. I think that should be enough. So I'm going to quickly go through these. 0 minus 4 is negative 4. And then if you take the absolute value of that, that's positive 4 plus 3 is 7. Let's see, that's going to be 6, 5, 4, 3, 4, 5. Okay, so at 0 it's 7. So 1, 2, 3, 4, 5, 6, 7. I'm going to use a different color. 1, 2, 3, 4, 5, 6, 7. So I'll plot a point right there. And then I will go ahead and plot those other points that I have. So basically what I'm getting out of my graph is I'm getting this V-shaped graph. And it goes on forever in both directions. So our graph is going to look something like that. So that's what we are looking for as far as part B. Let's go ahead and move on to the next segment. Part C wants us to create an input-output table to observe what the y values look like around the value x equals 4. So basically, we are wanting to make an xy table or an f of x table. And we want to see what happens for our output values when we choose x values that are very close to 4. So we might choose like 3.9, 3.99, 3.999. And then I want some values that are close to 4 on the other side of 4 that are greater than 4. So I want values like 4.001, 4.01, and 4.1, and things like that. But I'm not going to calculate these values by hand. This is something a calculator would come in handy for, and I'm actually going to compute these values in Microsoft Excel. So I'm just going to label this x, this y. So this is my xy table, or sorry, I keep calling it y. Maybe I should call it f of x. So I'll put 3.9, 3.99, 3.999, 4.001, 4.01, 4.1. And then what I want to do is I'm going to type equals ABS. So that returns the absolute value of, and then I'm going to go ahead and click this cell and then do minus 4, close parentheses, plus 3. And that's just going to go ahead and calculate the output value that we are looking for. So I'm going to go ahead and copy this formula down, and it'll give me these values. So notice that as our x value gets closer and closer and closer to 4, the output values are getting close to the number 3. Now let's see, maybe if I got even closer, so I'm going to scooch these down. What if I chose like 3.9999, and then I'm going to copy this formula down. So as we predicted, as I'm getting closer to 4 on my x value, my output value, or my f of x value, is still getting closer to 3. So let's do 3.99999999999. So this, even though I put 3.9999, with a lot of nines, Microsoft Excel is rounding it to 4, and then here it's rounding this number to 3, when in reality, it's really 3.00, a bunch of zeros and then a 1 at the end there. But all of that is to say, basically, as we approach x equals 4, the y values, or the output values, are approaching 3. So as x approaches 4, f of x approaches 3. Now, let's evaluate f of 4 and see what we get as our output. So f of 4 is going to be 4 minus 4, and then the absolute value of that, plus 3. So we'd be taking the absolute value of 0 and adding 3 to it. 0 plus 3, and that equals 3. So f of 4 is equal to 3, so that's nice. And, that's kind of hopefully what we expected after seeing this part here. So now that we've gone over this example, let's talk about the formal definition of a limit. So let f of x be a function defined on an open interval containing some real number c. Then we have this funky notation here, but the way that we read that is the limit of f of x as x approaches c equals L. The number L exists if we can make values of f of x as close to L as we desire by choosing values of x sufficiently close to c. When the values of f of x do not approach a single finite value L as x approaches c, we say that the limit does not exist. You may have noticed that it happened to be the case that the limit of f of x as x approaches 4 equaled f of 4 in the previous example, and we evaluated f of 4 to be 3. So in the previous example, the way that we would have written that is the limit as x approaches 4 of our function f of x was equal to 3. So that is how we would have notationally written what we described, or what we saw in the previous example. But this is not always going to be the case. Let's see an example where that is not the case in the next question. So example 2 wants us to find the limit as x approaches 1 of this function x minus 1 over x squared minus 1. So let's evaluate. So we have our function here, f of x is equal to x minus 1 over x squared minus 1. Let's go ahead and evaluate f of 1. So if we were evaluating f of 1, we just plug 1 into the function and see what we get as an output. So we'd get 1 minus 1 over 1 squared minus 1. So if we simplify the numerator, 1 minus 1 is 0, and then 1 squared minus 1 is also 0. And this thing, hopefully, you've been taught that when you divide something by 0, that thing is undefined. So let's jump into, before I used Excel, let's use another technology tool that will help us figure out the limit for this function. All right, so I'm here at desmos.com/calculator, and this is a really nice graphing utility where I can create a function. So x minus 1 over x squared minus 1. So here it's gone ahead and it's graphed that function for us. And hopefully you remember from pre-calculus that this is what we call a rational function. And then if I click this, I can change this function here into a table. And remember, we wanted to find the limit as x approached 1. So this allows me to plug in different values. And so I'm going to try 0.9, 0.99, 0.999, 0.9999, 0.99999. So what's happening here? Take a moment to kind of reflect and absorb. As my x values are getting closer and closer to 1, what's happening to these values here? Let's plug in 1. What happens? Well, as we saw earlier, recall from our notes here that we had 0 over 0, so that was undefined. And well, what if we plug in something like that? So 1.000001, what's happening there? So ask yourself, what's happening with the f of x values or the output values as x approaches 1? What is the y value approaching? If you said 0.5 or 1/2, you would be correct. So this is how we're doing it using a graphing utility. So coming back here, we would say that the limit as x approaches 1 of x minus 1 over x squared minus 1 is equal to 1/2. Now, it turns out that there's a way to do this algebraically and not necessarily using a graphing utility like we just used. So this requires some algebra skills. And I'm going to take a look at this function again, x minus 1 over x squared minus 1. And this thing here on the bottom, this is what we call a difference of squares. And hopefully you remember that from like an algebra or a pre-calculus class. What that allows us to do is it allows us to factor that. So we have x minus 1 over x plus 1 times x minus 1. And if we do that, then we can divide these terms out and be left with 1 over x plus 1, where x cannot equal 1. And the reason that x cannot equal 1 is because here originally if we plugged in 1, then the function was undefined. So now we can actually calculate the limit as x goes to 1 of this thing here, because here we can plug in 1. So we have 1 over x plus 1. And notice if I just plug in 1 here, it's going to give me the value 1/2, because I'll have 1 over 1 plus 1, which is equal to 1/2. So that's how you could figure out, and notice, these match up. That's how you can figure out that limit algebraically.